Calculus students, greetings. This lecture will be on optimization applications, which is where we will use calculus to find maximum and or minimum values of quantities that are relevant to certain scenarios. Now you must build a rectangular enclosure subdivided into two compartments and built against an existing wall. There are two tasks on this page. The first task is to minimize perimeter given area. The total area of the enclosure must be 400 square meters. Determine the dimensions that minimize the total amount of fencing and give this minimum amount. Here we see 6 general steps you should follow whenever solving optimization application problems. Step 1 is to draw and label a diagram, which is done for us on this page. This represents the existing wall mentioned in the problem, and we have a rectangular enclosure subdivided into two compartments, the left compartment and the right compartment. Now the fencing that we need would be these 3 segments, which all have the same length, and then this horizontal segment, which doesn't have necessarily the same length as the 3 vertical segments. This length I'll call X and would occur 3 different times, and I'll use Y to represent that one horizontal length. Now a few things we know. The total material, which we'll refer to as the perimeter, would be capital P is equal to, it would be X plus X plus X, or 3X, and then plus Y. And then the area of this enclosure and the total area, which means the area of both compartments combined, would simply be the product of X times Y. These are going to be 2 key equations for us moving forward with both tasks on this page. So returning to our task, the total area of the enclosure must be 400 square meters. So we are given that the area must be 400 and the area is found by calculating X times Y. Then we want to minimize the total amount of fencing. Well, that corresponds to our perimeter, and P is 3X plus Y. So we've accomplished step 2, which was to create a formula for the quantity you want to optimize. Step 3 is to express this quantity as a function of one input variable. Currently, perimeter is dependent on knowing both X and Y. We need to reduce this down to one input variable. The key to do this will be the given information about the area. Since the area must be 400, therefore Y is equal to 400 divided by X. This expression can be substituted in for the Y in our perimeter formula. So we get perimeter is equal to 3X plus 400 over X. And now perimeter is a function of one variable. You tell me X, and I can calculate perimeter. The next step is to determine the domain of the input variable. Since X is a length, we know it cannot be negative. Since X is in a denominator, we know X cannot be 0. Other than that, X can be any value. So our domain is that X, which is our input variable, must be greater than 0. Using technology, I've created a dynamic image of this situation. We have our enclosure against an existing wall. We see a variety of options, all of which have the same fixed area of 400 square meters. Our goal is to find the dimensions that will lead to a minimum amount of material required to make the enclosure. Step 5 is to use calculus to optimize the function over the domain. So begin by finding a derivative. The first derivative is 3. This term is 400 times x to the minus 1. Use the power rule, we get negative 400 x to the minus 2. So minus 400 over x squared. Now the domain of the derivative is also x must be positive. There are no values in the domain of the original function that are no longer allowed in the derivative. So there are no type 2 critical numbers. Now we look for type 1s by setting the derivative equal to 0 and solving for x. I'll begin by adding this fraction to the 0 side of the equation, multiplying by x squared and dividing by 3, and then taking the square root. And I only keep the positive answer because x cannot be negative. The square root of 400 is 20, so I could write this as 20 over rad 3, which is about 11.547. Next, we make a number line of our domain. X must only be positive, so we put 0 on our number line and ignore negative values of x. The critical number goes on here, and then we pick a test number between 0 and our critical number, so 1, and then a number bigger than our critical number, say 12, and test into the derivative. Plug 1 into this derivative expression, and we'll get 3 minus 400, which is clearly negative. So p prime is negative, meaning the function is decreasing. Plug 12 into the derivative and do 3 minus 400 over 12 squared, and a calculator gives us a positive result. So the derivative is positive, meaning the function p is increasing. So we know that the critical number produces a min value, and the perimeter will be minimized when we make a choice that x is 20 over rad 3, which will force the y-coordinate to be 400 divided by x, which will be 400 times the reciprocal of x, which will give us 20 rad 3, which is about 34.641. Both of these lengths are measured in meters because the area was measured in square meters. And now we can calculate the actual minimum perimeter, which was 3x plus y, 3 times x, which will be 60 over rad 3, plus y, which is 20 rad 3, which would be about 69.282, also measured in meters. So this choice of x and y are the dimensions that minimize perimeter, so we have resolved the task. Now to confirm this with technology, I'm going to type in capital P equals 3x plus 400 over x, and then adjust my scale so I can see it. Keep in mind, I'm not interested in this portion of the graph because this corresponds to negative values of x, so we could crop our function according to our domain that x must be greater than 0. If you click on the graph, Desmos will automatically find local maxima and local minima. Now the first coordinate is the x value that we found, 20 over rad 3, which is about 11.547. The second coordinate is a perimeter coordinate because the equation we're graphing is perimeter against x. Vertical axis represents perimeter values, and the horizontal axis represents x values. So the second coordinate we're seeing here is the minimum perimeter value, 69.282 approximately. Lastly, I want to mention that this middle portion, its position does not affect any of our work here. You can imagine subdividing this in different ways by moving where this middle fencing is. The total amount of fencing is unaffected, and the total area of the enclosure is unaffected. Okay, now let's consider the same scenario, same picture and relevant formulas, but now we're going to maximize the area given perimeter. Meaning, suppose that we are limited by how much fencing we can purchase. We have 1,000 feet of fencing. Determine the dimensions that maximize the total area of the enclosure and give this maximum amount. So we're on a budget and we want the biggest area possible. Here I'm using technology to see a variety of possibilities, but this time the perimeter is fixed, but we're getting differently sized enclosures. At one extreme, we use all the fencing to make just the horizontal leg and save no fencing for the 3 vertical legs. Hence, we would have no area. Another option is to commit all of our fencing to the 3 vertical legs, leaving no fencing left to make the 1 horizontal leg, again giving us a 0 area. So somewhere between these 2 extremes is the correct usage of our fencing so that the area will be maximized. All right, so this time it's the perimeter that's given, and that perimeter must add to 1,000 feet, and perimeter is given by 3x plus y. And our objective becomes to maximize area, and area is x times y. So steps 1 and 2 are done. Now step 3 is to express area as a function of one variable. Currently there are 2 variables here, so we use this given information here about perimeter in order to make a substitution and reduce from 2 variables to 1 variable. We'll do this by solving for y. Solving for y, we get y is 1,000 minus 3x. This expression gets subbed in to our area formula, giving us area is x times 1,000 minus 3x. Our domain, now again, x is a length, so x cannot be negative, but it could be as low as 0 in this case. If x were 0, that would simply mean that we use all 1,000 feet of fencing for the y length, but that would produce an area of 0, so not ideal. The largest x would be 1,000 divided by 3. This would be where y is 0. In other words, we use none of the fencing for the y length, and we use all 1,000 feet of fencing for the 3x lengths, which means each x would be 1,000 divided by 3. This would also produce an area of 0, because y would be 0, so not ideal. Now, before I differentiate area, I'm going to distribute the x and rewrite this. So we get 1,000x minus 3x squared. Right away, I can recognize that this is a quadratic function with a negative leading coefficient. So I know the basic shape will be an upside-down parabola. So next we do the derivative of area with respect to x. So a prime will be 1,000 minus 6x. The domain of this derivative ordinarily would be all real numbers, but we will force it to be limited to the domain of the original. In other words, there are no values in this domain that cannot be plugged into the derivative. There are no type 2 critical numbers. So we only look for type 1 critical numbers. So set it equal to 0 and solve for x. I'll add the 6x over and then divide by 6. 1,000 divided by 6 can simplify to 500 thirds, which is approximately 166.67. And our unit this time, we changed our unit to feet instead of meters. Next, we would do a number line that reflects our domain from 0 to 1,000 thirds. We found a critical number at 500 thirds. An easy test number in the first subinterval would be 1, and then in the second subinterval, perhaps a 200. Plug 1 into a prime right here. So we'd get 1,000 minus 6. We get a positive result. So a prime is positive, meaning the function is increasing. Plug 200 into a prime. That's 1,000 minus 1,200. That's negative 200, but negative is what matters, and the function is decreasing. So we do have the location of a max. So if x is 500 thirds, then y is, using our relationship between y and x up here, substitute 500 thirds in for x, and we wind up getting 500 feet for y. And then the max area will be x times y, where x is 500 thirds, and y is 500, so we get 250,000 thirds, and the unit here would be square feet. With technology, I'll type in the equation for our area as a function of one variable. I'm going to change my scale. Next, I'll crop the function from 0 to 1,000 thirds. Now keep in mind the vertical axis represents area and the horizontal axis represents x, as depicted in our drawing. But the maximum area will occur when x is this value, and the maximum area will be 83,333.3 repeating, which is a decimal version of the answer we got, 250,000 thirds. Okay, let's go to the next page. A rectangular sheet is 6 feet by 8 feet. You want to make an open box by cutting equally sized squares from each corner and folding up the flaps. Determine the size of the squares that need to be removed from each corner in order to maximize the volume of the box and give this maximum volume. This rectangular sheet is 6 feet by 8 feet. We're going to remove 4 equal squares from each corner. Let's say each of them is x by x. Then fold up the flaps to make a box that has no top. The question is, how big should the squares all be so that the resulting box has maximum volume? Often we label the dimensions of a rectangular box as length and width for the base and then a height. And given this labeling, the volume would be the product of these 3 dimensions. We have a quantity, the volume, which we want to maximize. Step 3 will be to express volume as a function of only one variable, and that variable I will be using will wind up being x. From one picture to the next, this length right here will correspond to the width of our box. This segment will be the length of our box. The height of our box will be dictated by the side length of any one of these 4 identical squares. That length is given by x. This blue segment would have a length that began with 6, but we removed x from each end. So we removed 2x. And this green segment began with a length of 8, but again we removed x from each end. So remove 2x. So our width can be described as 6 minus 2x, and our length as 8 minus 2x. This allows me to express volume now as a function of one variable. The length is 8 minus 2x, the width is 6 minus 2x, and the height is just x. Using technology, you can see that as we change the size of the squares that we cut out, that the resulting box will have different volumes. So x can vary from 0, meaning don't remove any corners. X can be no more than half of 6, because if it were, you would not be able to remove 2 such squares from the shorter side. So our domain in this will be x must be between 0 and 3, and that 3 is half of the shorter side. And now I want to go to step 5, where we use calculus. Before I differentiate v, I'm going to simplify it by distributing. I'll begin by FOILing. So we have 8 times 6 is 48. 8 times negative 2x is negative 16x. Then we have minus 12x plus 4x squared. And all of this still needs to be multiplied by the x on the outside. These 2 middle terms are similar, so we can combine them. So v is 48 minus 28x plus 4x squared, and then times an x still. Distribute that x, and we get 48x minus 28x squared plus 4x cubed. Now I am ready to differentiate. V prime will be 48 minus 56x plus 12x squared. The domain of this derivative will be the same as the domain of the original, because there are no values of x in the original domain that can not be plugged into this derivative. So there are no type 2 critical numbers. So we must now try to find the type 1 critical numbers by setting the derivative equal to 0. But first I'll do some factoring. I'll factor out a 4 and put the x squared term first. So 3x squared minus 14x plus 12. This quadratic will not factor using rational numbers. So we do need to resort to the quadratic formula. A is just 3, b is negative 14, and c is positive 12. So x will be negative b, so 14, plus or minus the square root of b squared. Negative 14 squared is 196, minus 4ac, which will be 144, all over 2a, which will be 6. So we get 14 plus or minus square root of 52, all over a 6. 52 is 4 times 13, so rad 52 will be 2 rad 13. Now I can factor a 2 out of the numerator and cancel with the denominator, giving me 2 answers, 7 plus or minus rad 13 over 3. When you reach for a calculator and convert these to decimal, you get 2 answers, approximately 1.131 and approximately 3.535. This second one, though, is not in the domain, so it's not a relevant critical number. Next, we do a number line that represents the domain. So from 0 to 3, we put our only critical number on it, which was 7 minus rad 13 over 3. Then we pick test numbers. A 1 is in this first subinterval, and a 2 would be in this second subinterval. Now plug 1 into this derivative, and we will get 48 minus 56 plus 12. That's 60 minus 56. That's a positive result. So v prime is positive, meaning the v function is increasing. Plug 2 into the derivative. 2 squared is 4 times 12 is 48, plus another 48 is 96. But 2 times negative 56 is negative 112. So in the end, v prime will be negative, and we get that volume is decreasing. So we do have a max volume at this critical number. So in summary, when x is 7 minus square root of 13 thirds, which is approximately 1.131 feet, the max volume will be v of this number, which we'll use technology to calculate. I'll type in the expanded version of v, which was 48x minus 28x squared plus 4x cubed. I'll use function notation, so I'll say v of x. I'll say our critical number, c for critical, equals 7 minus square root of 13 all over 3. So plugging this value into the v function, we get approximately 24.258, and this will be measured in cubic feet. Now we have a graph of our function. I'll change the scale so we can see it. I'll restrict our domain. X had to be between 0 and 3, and Desmos finds this maximum for us. Keep in mind that the vertical axis here represents volume of the box. The horizontal axis represents x, which is the side length of the squares that are removed from each of the 4 corners. So this first coordinate is a side length of those squares, and the second coordinate is a resulting volume of the box. Okay, let's go to the next page. You must design a box with no top, a square base, and a volume of 10 cubic feet. The base of the box costs $3 per square foot, and the sides cost $2 per square foot. Find the dimensions of the box that minimize the cost of the material needed to make the box. Give this minimum cost. So the base of this box is square. I'm going to use, therefore, x and x to represent the length and width. The height, I don't know what it is, so I'll use a different variable for that, h. So the volume of such a box would be x times x, or x squared, times h. It's also given that we need the volume of this box to be 10 cubic feet. Now what we want to do is we want to minimize cost, and I'll use capital C for cost. So we need to come up with an equation for cost. Well, the base and the sides don't cost the same amount of money per square foot, so it's helpful to deconstruct this box. The base costs $3 per square foot, and each of the 4 sides cost $2 per square foot. Now my goal is to figure out the total cost to make this box. So I'll use a table to organize the costs for each portion. I want to keep track of the area measured in square feet, and then the total cost measured in dollars. And for the base as well as for all 4 sides, since the 4 sides are all equal. Now the base has dimensions x by x, so its area is x squared. Each side has dimensions x and h, so the area of each side is x times h, and there are 4 of them, they're all equal, so we get 4xh as the area of all 4 sides. Now the cost for the base is $3 per square foot times x squared square feet. So simply 3x squared measured in dollars. And the cost of all 4 sides would be $2 per square foot times 4xh square feet. In other words, 8xh dollars. So our total cost will be C equals 3x squared plus 8xh. Currently, our cost is dependent on both x and h. We now need to express cost as a function of one variable, and the ticket to doing this will be our given information about the volume. The fact that 10 must be equal to x squared h allows me to say that h has to be, therefore, 10 divided by x squared. So we can substitute 10 over x squared in for the h in our cost function, and we get cost is equal to 3x squared plus 8x times 10 over x squared. And simplify this, we get cost is 3x squared plus 80 over x. The domain of this, x can't be negative because it's a length. If x were 0, your volume would be 0, but we need the volume to be 10. So x has to be positive, but there is no upper limit. And now we use calculus. Let's find the derivative. C prime is equal to 6x, and the derivative of 80 over x, that's minus 80 over x squared. The domain of this will match the domain of the original. There are no type 2 critical numbers. So we look for type 1s by setting the derivative equal to 0 in solving. I will add this fraction over to the other side. So we have 80 over x squared equals 6x. Multiply by x squared and divide by 6. That gives me x cubed is equal to 80 over 6, which is 40 thirds. And now take a cube root, which is approximately 2.371, and this will be measured in feet. This is our only critical number. So make a number line that reflects our domain. Our domain starts at 0, but exclusive, and goes to infinity. We put our only critical number on it and pick some test numbers that are easy. So a 1, and I'll pick a 10. That will be easy to plug into our derivative. So looking at C prime, we plug 1 in for x, we get 6 minus 80, we get a negative result, meaning the C function is decreasing. Now we plug in 10, we get 60 minus 80 hundredths. That's clearly a positive number, meaning that our cost function is increasing. after the critical number. So we have the location of a minimum. Now we were expected to find the dimensions of the box. So we've already found the x value, these two. We now need to calculate h using the fact that h has to be 10 divided by x squared. So it'll be 10 divided by, this could be written as 40/3. The cube root is 1/3 power, but then when you square that, you now have a 2/3 power. This will be approximately 1.778 feet. And then lastly, we're expected to find the actual minimum cost. I could do this a variety of ways. I could use this cost equation and substitute in both x and h and calculate cost, or I could use this cost expression and substitute only in x. This is what I'll do. So the cost will be 3 times x squared. X is 40/3 to the 1/3 power. You square that, you get a 2/3 power, plus 80 over, and then x is 40/3 to the 1/3 power. And this is a minimum cost. I'll use technology to help me with this. As a function of x, the cost function is 3x squared plus 80 over x. Then I'm going to crop it for x being positive, and then change my viewing window. We found the critical number, I'll call it a, was 40/3 to the 1/3 power. The height of the box was 10 divided by this value squared, and then the minimum cost will be the c function evaluated at this critical number a. So we get about 50.606, and this will be measured in dollars. Now in our graph, keep in mind that the vertical axis is cost, and the horizontal axis is x, which is the side length of the square base. If the base is approximately 2.37 feet by 2.37 feet, then the resulting cost to make that box will be approximately $50.606, our minimum cost. Okay, let's go to the next page. A 6-foot tall painting is hanging on a wall, and the bottom of the painting is 1 foot above eye level of an observer. Find how far from the wall the observer should stand to maximize how much the painting occupies their field of vision. Give this maximum angle. In our drawing, the painting is represented by this line segment and is 6 feet tall. And the bottom of the painting is 1 foot above horizontal eye level of the observer. Now, this observer will have the best view of the painting if they position themselves in such a way that this angle theta is maximized. Using technology, you can see that as the person approaches the painting, that the angle will have some maximum before it decreases again. So our goal is to maximize theta by controlling how far the person should stand from the painting. We'll call that horizontal distance x. This triangle right here is not a right triangle. However, this triangle is a right triangle, and so is this triangle. Now, because of those right triangles, I'm going to adopt the following strategy. We will find an expression for this angle, which I'll call alpha, and then another expression for this angle, beta. And then we can see that theta can be expressed as the angle alpha minus the angle beta. So looking at the big triangle and the angle alpha, the height of the big triangle would be 6 plus 1, or 7 feet, and the horizontal leg would be x feet. So we know that the tangent of alpha would be equal to opposite 7 divided by hypotenuse x. So alpha itself would be the arctangent of 7 over x. Looking at the smaller right triangle with its angle beta, the height of that triangle is only 1 foot, and the horizontal leg is x feet. So we know that the tangent of beta is 1 over x. In other words, beta is the arctangent or inverse tangent of 1 over x. This will allow me to express theta directly as a function of the distance the person is from the wall. Alpha is arctangent of 7 over x minus beta is arctangent of 1 over x. In the domain of this function, we cannot let x be 0. Clearly, if x were 0, the observer would have no good look at the painting. But in theory, the observer could be as far from the painting as infinity. And now that we have theta expressed as a function of one variable x, we can differentiate and find critical numbers. So theta prime will be equal to. Now recall that the derivative of arctan u is u prime over 1 plus u squared. So when I differentiate arctan of 7 over x, I get the derivative of 7 over x. That's 7x to the minus 1, which is negative 7x to the minus 2, or negative 7 over x squared, over 1 plus, and then the square of 7 over x, which will be 49 over x squared, minus the derivative of 1 over x is negative 1 over x squared, and then all over 1 plus, and the square of 1 over x is 1 over x squared. Next, I recommend simplifying both of these by multiplying them each by x squared over x squared. So we get theta prime is equal to negative 7 over x squared plus 49. Then we have this subtraction of a negative, so this will switch to addition, plus, and then multiplying by the red x squares, we get 1 over x squared plus 1. Now the domain of theta prime will be no more restrictive than the domain of the original function, so we have no type 2 critical numbers. So we will set the derivative equal to 0 and solve for type 1 critical numbers. This fraction I will add to the other side. Now I will cross multiply. 7 times this denominator will be equal to x squared plus 49 times this numerator. Distributing, gathering like terms, subtract x squared from both sides and subtract 7 from both sides. Divide by 6 and take a square root and keep only the positive. So we get x must be the square root of 7, which is approximately 2.646 feet. This will be our only critical number. Now we do a number line reflecting the domain of the function. So 0 exclusive up to infinity, and we put our only critical number on it. A number less than this is 1, a number greater than this is 3, and we plug these into the derivative. So theta prime of 1 will be equal to negative 7/50ths plus 1/2. Well, 1/2 is 25/50ths, and I can see we get a positive result out of this. So theta prime is positive, so theta is increasing on this subinterval. Now plug 3 into the derivative. We get negative 7 over 3 squared is 9 plus 49 is 58 plus 1/10. Getting a common denominator, we'd have negative 70 plus 58 580ths. This is enough to see that the result will be negative, so theta is decreasing on this subinterval, suggesting that theta will be maximized when x is this critical number, square root of 7. So the observer should stand square root of 7 feet from the wall, and then the max angle will be theta of square root of 7. So we plug square root of 7 into this expression. Now I'll use technology to help. So I graph the function. I'm using capital T for theta. T of x equals arctan of 7 over x minus arctan of 1 over x, and I limited it to x being positive. Change my vertical scale. I'll use C for critical number, and it was the square root of 7. Now plug square root of 7 into our T function, and we get a max angle of about 0.848, and this would be measured in radians. Keep in mind that the vertical axis of our graph represents theta, and the horizontal axis represents x. So this first coordinate is an x coordinate. The observer should be 2.64575 feet away from the wall in order to have a maximum theta of around 0.84806 radians. Okay, let's go to the next page. You need to go from point A on the shore to point B inland. Your speed along the shore is 5 miles per hour, and your speed inland is 3 miles per hour. Each grid is 1 mile by 1 mile. Find the path that takes the least amount of time and give this minimum time. So point A is on the shore, point B is inland. Ordinarily, the shortest path between them would be a straight line. However, this would require you to travel while being inland the entire time, which is a slower speed, 3 miles per hour. Because it is faster to go along the shore, it might be better to go some of the way along the shore at a faster speed before cutting inland to reach point B. Or perhaps we should go all the way across the shore until we can turn 90 degrees and go directly to point B, thus requiring the least amount of travel inland. Maybe this will be the fastest way to get there. Now each grid is 1 mile, so we can see that point B is 4 miles downshore before we would need to cut inland and go 1 mile. What we don't know is how far along the shore we ought to travel. So let's call this distance x before we turn inland and then go a distance y. Now recall that distance traveled is constant rate times time. For example, if you're going 3 miles per hour and you travel for 2 hours, then you would multiply these to get a distance traveled of 6 miles. I'm going to use this relationship and create a table for the travel along the shore and the travel inland. We'll keep track of the distance measured in miles, the rate or the speed in miles per hour, and then the time measured in hours. And this will be for along the shore and then inland. Now, along the shore, the distance would be x miles. The rate along the shore is 5 miles per hour. And if distance equals rate times time, then we know that time can be calculated by doing distance divided by rate. So the time here would be x divided by 5. Now, the distance inland is y. The rate inland is 3 miles per hour. So we do the distance divided by the rate, and we would get the time. So let's say that the total time, we use capital T, will be equal to the time along the shore, which is x over 5, plus the time inland, which is y over 3. So we've created a formula for the quantity, total time, that we want to optimize, in this case, minimize. However, there are 2 variables. As inputs, we need to reduce this down to 1 input variable. The key to doing this will be at this right triangle. This length right here would be 4 miles minus x. It would be the total distance downshore minus the distance that we walk along the shore. So looking at that right triangle, we know that the hypotenuse squared will equal the leg squared plus the other leg squared. In other words, y can be found by doing the square root of 1 plus and then 4 minus x squared. This expression can be substituted in for this y in our time expression. So the total time can be written as 1/5 of x plus 1/3 of this function y. The domain of this function will be that x must vary somewhere between 0 and 4. It's possible for x to be 0, meaning we don't do any walking along the shore, we walk inland only, or for this value x to be as much as 4, putting us directly south of point B before we cut inland. It would not make sense for x to be more than 4 or for x to be negative, for obvious reasons that would only add time to our travel. Now we're ready for a derivative. T prime will be equal to 1/5 plus 1/3, and now we need to differentiate this radical. Recall that when you differentiate the square root of u, using generalized power rule, you wind up getting u prime over 2 square roots of u. So in the numerator, I need to put the derivative of what's inside the radical, which is called the radicand. The derivative of the 1 will be 0. I do need to differentiate this part using generalized power rule. So I would get 2 times 4 minus x raised to the 1 power, and then times the derivative of the inside, which is negative 1. And all of this will be over 2 times the square root of the original function. This denominator can never be 0, no matter what x is. So we have no restrictions on x, meaning the domain of our derivative is the same as the domain of the original, and so we do not have any type 2 critical numbers. So instead, we're going to look for type 1 critical numbers by setting the derivative equal to 0. Before that, we do some simplifications. These 2's are going to cancel, and this negative, I'm going to change this sign to subtraction instead. So we have the equation 0 equals 1/5 minus 1/3. The numerator is 4 minus x, and the denominator is still this radical. Now I'm going to add this fraction to the other side of the equation. Now I'm going to cross multiply by multiplying this denominator to this numerator and set that equal to the product of this denominator and this numerator. That gives me 5 times 4 minus x is equal to 3 times this radical. Next I will square both sides, giving me 25 times 4 minus x squared equals 9 times, and then this radical will go away and become simply 1 plus 4 minus x squared. Next I'll distribute this 9 to get rid of those outer parentheses. This term I'll subtract to the other side, and because it's similar to this term, I can just subtract the coefficients. So we have 25 minus 9, and we get 16. 4 minus x squared is equal to 9. Now divide by 16, take the square root. We'd have plus or minus, and the square root of 9/16 is 3/4. Next I'll subtract 4, so we have negative x equals negative 4 plus or minus 3/4, and then multiply everything by a negative. So we get x equals 4 plus or minus 3/4. That gives me answers of 4.75 and 3.25. One of these is not in our domain. It is not a choice of x we would want to make because that would make us walk past point B and then backtrack inland, which obviously would not give us the shortest amount of time. So the only critical number in our restricted domain is 3.25. We do a number line next. On goes the critical number, and we need some test numbers. 1 and perhaps 3.5 are going to be good test numbers. Now we plug these into the derivative and determine whether the derivative is positive or negative. We remove this reminder and put our work in this space. T prime of 1. And I'll use this simplified version of the derivative right here. We would get 1/5 minus 1/3. The numerator would be 3, and the denominator would be 1 plus 9, which is 10, inside a radical. So we get 1/5 minus 1 over radical 10. This is a negative number, which can be confirmed with the calculator, meaning that t prime is negative, so capital T, or time, is decreasing. Now, as my second number, instead of using 3.5, I can use the right endpoint as a test number. Because the domain was artificially cropped from 0 to 4, 4 is a number that would have been between these two critical numbers, so I will use the 4 as my test number just to keep the mental work easier. Capital T prime of 4 will be equal to, when you plug 4 into x here, that will put a 0 in the numerator, which will zero out this entire fraction. So we're just going to get the 1/5, which is clearly positive. So the capital T prime is positive in this subinterval, meaning the capital T function is increasing. This gives us a minimum value of capital T at this critical number, telling us that we should walk x equals 3.25 miles along the shore before we cut directly to point B. And the total time when x is 3.25 we'll plug 3.25 into this capital T function. I'll use technology to help. So type in the capital T of x function, crop it. We see the critical number was when x was 3.25, and I'll evaluate capital T at this critical number. And we get a decimal, which can be converted to a fraction, 16/15. And this will be measured in hours. And this is the minimum travel time. In our graph, I'll change our scale. Keep in mind the vertical axis represents total time traveling, and the horizontal axis represents how far along the shore we should walk before we cut towards point B. So this minimum point suggests we should walk 3.25 miles along the shore, and in so doing, the total time of travel will be 1.06 repeating hours, which in fraction form is 16/15 hours. So 1 hour and 1/15 of an hour. 1/15 of an hour is 1/15 of 60 minutes, which is 4 minutes. So 1 hour and 4 minutes is our minimum travel time. All right, this concludes our lesson on optimization applications.